again, and we're going to talk about the midpoint rule. So this is the formal definition, which looks a little confusing. So I just added in this. You don't have this slide on yours. But we've talked about over and under estimates, right? And if I'm looking at this first one, okay, I was looking from 0 to 2. What was my change in x on that one? How much did my x go up each time? A half. All right, and would this one have been an over or an under estimate? Under, we can see those rectangles are under the curve. In this section, instead of saying over and under, it kind of talks in terms of left and right-hand sum. Would this one be a left or a right-hand sum? So the first interval starts at 0 and ends at 1/2, but I used the height at 0. The next one is from 1/2 to 1, but I used the height at 1/2. The left sum. Okay, so then you would have used the 1.5, or sorry, the 1 and the 1.5, and that would have stopped. This one, my change in x is still 1/2. Is this one an over or an under estimate? Over, because we see the rectangles are higher than the curve. If I were asking a left or right sum, so look, starting at 0, ending at 1/2, I used the height at 1/2. This one I used the height at 1, the 1.5, and the 2. So was this left or right? Right. So basically, since we're going up by 1/2, the left-hand sum uses the left endpoint, the right-hand sum uses the right endpoint. What do you think the midpoint sum would use? The middle. Which of the three do you think would be the most accurate? The midpoint. All right, so this is what it would look like as the midpoint. So we can see it is much closer, but you look between 0 and 1/2, we would use a 4. Between 1/2 and 1, we use 3/4. Okay, so that's what a midpoint sum is. So now we could do left, we can do right, we can do midpoint. Midpoint is the most accurate of the three. So let's look at this problem. Evaluate the Riemann sum for f of x equal x cubed minus 6x, taking the sample points to be the midpoints on the interval 0 to 3 with 6 rectangles. So my change in x, ending minus beginning divided by 6, because 6 rectangles. So my change in x is 1/2 or 0.5. So if you think about what's happening, 0, we're going up by 0.5 every time, right? You don't have to draw this picture, but since it's our first example, I'm doing it to kind of illustrate what's happening. So this would be how we're breaking up the x-axis. If I want to estimate this area, so we know the area is the area of a rectangle, length times width. All these rectangles have a width of 0.5. And we're adding up 6 of them. All right, if I were doing a left-hand sum, what would be the first number I plugged in? 0. If I were doing a right-hand sum, what would be the first number I plugged in? 0.5. For the midpoint, we have to say, okay, I want the middle of this. So what's in between 0 and 0.5? So the first x I plug in is 0.25. So we have 0.25 cubed minus 6 times 0.25. Now, once you get the first point, everything else is the same. My change in x is still 0.5, so I add 0.5. You could go through and calculate the midpoint of every one, but we know if we have the first one, the next one just goes up by 0.5, so it'll be 0.75 cubed minus 6 times 0.75. 0.25 cubed minus 6 times 1.25. 1.75 cubed. 6 times 1.75. 2.25 cubed minus 6 times 2.25. And 2.75 cubed minus 6 times 2.75. So I'm going to plug this in. I get -7.03125. I don't really know if this is over or under. It will really just depend on the situation. But I do know that it's more accurate than just doing the left or the right hand sum. All right. Any questions on that one? Does it seem kind of familiar? Hopefully. Let's do a couple review problems from Friday, or at least one. If I ask you to evaluate this integral, all right, we had to write these using the limit of the sum notation, right? So we needed our change in x. Isn't this the same function that we were just doing? Okay, we're going to get the real answer now and see how close our approximation was. So my change in x is our ending minus our beginning divided by b. In rectangles now, because I know the more rectangles I have, the more accurate it will be. So if I'm trying to find the real answer, I have to have an infinite number of rectangles. My x sub I, what I'm plugging in is our starting point plus multiples of the change in x. So we're starting at 0 plus 3 over n times I, which is just 3 over n I. So we're going to do the limit, same goes to infinity, of the sum from 1 to n. Remember, this expression replaces that integral. Then we replace these x's with the x sub i's. So that's 3 over n I cubed minus 6 times 3 over n I. And what do we do about this dx? What do we replace it with? Remember, that's how we went back and forth between the integral and the limit of the sum. So now we're just going to work this out. So if I cube 27 over n cubed I cubed, that's 18 over n I. Distributed by 3 over n. 81 over n to the 4th I cubed minus 18 times 3 is 54 n squared I. What comes next?
Put in the shadow. your I, like, what did I, like, n plus one?
Yeah. We add up those i's, and when we do that, the summation drops. So 81 over n to the fourth. What's the I cubed formula?
Or n squared times n plus one squared.
Over 4 minus 54 over n squared times I, which is n times n plus 1 over 2. I kept telling you guys last week, this is really just a bunch of algebra. We're doing a lot of simplifying here. I can cancel an n squared there. FOIL. This one here, an n. 4 divided by 2 is 27. So I'm going to distribute and divide. So 81 over n, 81 n squared over 4 n squared, so 81 over 4. Minus 162 n over 4 n squared. You could reduce, I'll just cancel an n. Plus 81 over 4 n squared. Here, distribute the negative. So minus 27 n over n. Minus 27 over n. And we know anything with an n on the bottom turns into 0. So I just get 81 over 4 minus 27. Which is negative 6.75. All right, on the previous example, what did we estimate the area to be? Negative 7.03125. The true area is negative 6.75. So we were a little bit off, but not a ton. So we can estimate it using the left, right, or midpoint sums. We can find it exactly by doing the limit of the sum. This is just time consuming. Any questions on that one? I'm going to do one more example for today. So just one more practicing setting up a midpoint rule. N is 5, and I want to use that to approximate the integral from 1 to 2 of 1 over x dx. So if I were really trying to find it, I would have to do the limit, does the number of rectangles approach infinity? But I'm approximating it using 5 rectangles. My change in x will be what? It's your ending minus your beginning divided by the number of rectangles. So 1/5 or 0.2, whichever you want to plug in. All right, so when I'm setting this up, the area is length times width. They all have a width of 0.2. So we just need the 5 heights of these rectangles. All right, so this is what I like to do. I like to just draw a very little piece. So if I'm starting at 1, and I know that because that was the beginning of my interval, it increases by 0.2, so the next one will be 1.2. If I were asking for a left sum, what would be the first number you would plug in? 1. If I asked for a right sum, what would be the first thing you plugged in? 1.2. I want the midpoint, so we need the middle. Add them up, divide by 2, just average the 2 if you can't tell, but it would be 1.5. So that will be the first number I plug in. Just putting it in for my x in this expression, the 1 over x. Now, you could go through and calculate it every time, but I know x just goes up by 0.2 each time. So the next one would be 1.3, 1.5, 1.7, 1.9. We know if we did another one, it would be 2.1, and that's too much, because it stopped at 2. So that's a quick check to make sure we were right. And then 6919 for our approximate. Maybe, nobody looks like they agree with